have their own messages. They receive a message which is smaller. In this case, they adopt the message and they add the code and want to. So this way, so this very similar to this transaction. Now a bridge sends the BPDU only on a LAN only if its BPDU is smaller than any BPDU that it has received from this LAN. In this way, the number of messages that are sent is actually quite small. All right, and then it goes, yeah, and then they converge. So the rule is then a bridge will send its BPDU on a port only if it is better, advertised as better than any BPD that it has received on that port. Having an output is small. So the smallest number always wins, and then you can indicate your port. Yeah? So for a bridge, if a bridge receives the number it has received, the smallest BPDU, that port becomes the root port because it points to the path to the root. If the bridge is sending out a BPDU on one of its ports, that means then that its BPDU is smaller than anything that other bridges send on this LAN. Then the bridge, then these ports were sending out its BPDU. These are then become the designated ports. So you have the root port and the designated ports. All other ports start to be blocked ports. So you have the ports that are designated ports and the root port. These ports are put in a forwarding state, meaning the bridge will send packets on these, will transfer packets on these ports. Ports that are not designated ports or root ports, they are put in a blocking state, and that has the effect, yeah, that having here this picture here. If a bridge is not root, or if a port is not root port or designated port, this one will be blocked. And so what you're doing then, the spanning tree essentially consists of just connecting the LANs and the bridges and connecting root ports to designated ports. Now the root bridge here only has designated ports. So this bridge, you see here, if data is now forwarded, for forwarding traffic between LANs, there's only one bridge responsible. You see here that traffic from kind of using the spanning tree, the traffic actually takes a much longer route than what the minimum path is. This port here will be blocked. It's not part of the spanning tree. So if you're sending traffic from this LAN here to something on LAN 2, you actually could have a shorter path by going LAN 1, this bridge here, and then LAN 2. But this is blocked, so traffic will not flow this way. So the traffic between LAN 3 and LAN 2 will go through on LAN 1 and LAN 5, so it takes the longer path. That is a consequence of the spanning tree. You're not using always shortest path, because you're always going, that's one consequence. The other is that by necessarily the root bridge, the bridge that is the root bridge gets the most traffic. So it's important that that bridge is well located as well as the active switch that you have. So if you're looking at Ethernet switches, they come in 100 megabit with 1 gigabit ports, 1 gigabit ports with 10 gigabit uplinks, and then 10 gigabit ports. So that is what you're buying today. Where a 10 gigabit switch is relatively expensive. 10 gigabit switch with 12 or 8 ports cost something like $15,000, $20,000. If you're buying a 100 megabit switch with 16 ports, they almost $30 or $50. Let's see, shouldn't be saying that. One distinguishes there between managed switches and unmanaged switches. So if you're buying switches for a company, so if you're talking an enterprise network, these would always be managed switches. That means they can be configured. So they run essentially an operating system like iOS, like Cisco. You can go in and configure. Versus unmanaged switches, these are just these devices that you pick up in a computer store, and you never configure anything on that. They may be running the spanning tree protocol, but they don't cannot be configured. The ports cannot be configured for anything like that. So then these bridges would cost maybe like, for 48 ports, maybe $1,000. If you're getting gigabit, no, actually, if you're buying 48 ports, a switch with 48 ports, all gigabit ports with 10 gigabit per second uplink. Uplink means that, for higher concentration to connect multiple such ports, then this will be the order of a few $1,000, $3,000, $4,000. So this is kind of just give you a sense of the process. Anyways. All right. Then we computed an example. Does anybody have questions on the computation of this example? If not, it's not very hard to see. So that's the spanning tree algorithm. The next piece that I want to talk about, we're not doing this in the lab. Because frankly, when I wrote the book, it was not on my horizon to do this. But it's something that probably should have been in the lab somehow. There's a reason. VLAN. In talking about switch configuration in the ECE department, everything is about VLANs. Ports. Ethernet ports. I can't find the Ethernet ports somewhere else. Every Ethernet has Ethernet ports. Ethernet ports are assigned to VLAN. So VLAN has become the main method to organize. VLAN is the main method to organize switch Ethernet networks that have an overlaying routing architecture. VLAN stands for virtual LAN. Virtual LAN. And this is how it comes about. So if you have a network, if you're having a network here where you have switches here and switches here, everything is Ethernet switch, then you essentially create one large LAN. One large local area. Which means that they're running the spanning tree algorithm, but what it also means in a LAN is that broadcast traffic, if one packet here sends the broadcast packet, that broadcast packet is kind of going to all computers in this large LAN. This can create a problem. Local broadcast traffic, ARP traffic, is broadcast traffic. So a lot of ARP traffic. So setting up other than just the size of the spanning tree and the possibility of creating a bottleneck at the root bridge, broadcast traffic in large local area networks that use switched Ethernet. So these are switched LAN switches here. They all run the spanning tree protocol between them, so they can get traffic from here to here. It's just going this path here. So that can create a problem. Now, if you're doing subnetting helps. Subnetting means you're using IP to separate broadcast domains. So what you're doing here is you have all the you have all the devices connected to a switch that are closely located. Let's say it's an area of the floor of a larger building. That area of the floor, like the northwest, all the devices, hosts that are connected to the same Ethernet switch, they are being assigned a subnet, an IP network address, and then the router transfers packets between them. And you're using routing to get packets between here and here. So if you're sending packets between LAN 1 and LAN 2, it passes through the router. In this way, routers don't carry the broadcast traffic, like ARP packets are not carrying across. So here, the problem is solved. So the broadcast domains are separated. And each smaller lab is one subnet. There's an IP network. The drawback of this is that the assignment of a LAN, the assignment of a host to a broadcast network is determined by its location. Like something is here, this is here the wiring plan, you're going here into a switch. Yeah, the way this goes is, this one here goes into, connected to the wall, into an Ethernet jack. Then there's the wiring going into, probably on the floor or in the basement, going into a rack where a switch is located, and then this is then the location there. So what is not possible here is that you cannot build working groups. Working groups where you have one side in a different building belonging to the same, one side in one group in computers in one building, being on the same broadcast domain as the systems in the same building. And a good example of that is actually Central Fleming and the Bain Center. Both buildings have offices from the computer science department and the ECE department. So they would, the CS people, they have their own file server, they access their file server, they may want to be on the same broadcast domain, same for ECE folks, but then your wiring is such that you cannot do this, so this is not very flexible. So that's where VLAN comes in, and I just realized that this picture here is not, I need to do something else. Sure, I need to do this picture. Haven't launched my time, does it? What I'm going to do is I will So this is where virtual local area networks, or VLANs, come in. It's essentially the ability to create broadcast domains where the assignment of the broadcast domains is left to the administrator. It becomes configurable. In this way, it is possible to define a broadcast domain that does not depend on the location of the host and the switch. So a VLAN is essentially the same, just creates a broadcast domain. Meaning that if you're sending a broadcast packet, if this computer sends a broadcast packet, it will be received by these two systems, but not by the computers on LAN 2 and LAN 3. So these devices here, the VLANs here, they operate the same way as if you have these machines plugged into the same hub. And we can send it to one, you can send a broadcast packet without traffic. Now, from this computer to this computer goes right into the Ethernet switch, like these boxes here, these are the Ethernet switches, this is the router, the IP router, goes into this switch, to the other switch, to over here. It does not go through the router. Traffic from this computer to this computer here, see they're connected to the same switch, goes from here into the switch, into the router, back into the switch, into the LAN. Because they are different subnets. That's Peter. So, and so in this case here, what you're saying is here essentially is you're completely decoupling working groups that are in the same kind of broadcast domain from the location. Fantastic. Lots of flexibility. Yeah? For example, I have a subnet from the University of Toronto, small subnet. The subnet is mostly computers in my research lab, which are on the 7th floor of the Bain Center. But then I have a computer in my office, as well as a printer outside my office. They're going into an Ethernet jack. They are put on the same subnet as my computers in the 7th floor of the Bain Center. The way it's done is that the ports where I connect, these ports are assigned to the same VLAN as the ports that are used in my research lab on the 7th floor. Okay, how is this done? Well, it requires VLAN switches. If you want to set up VLANs, you need to run Ethernet switches that are VLAN enabled. Yeah, and one way, and I'm using here colors to indicate different VLANs. It's essentially that one assigns VLANs to ports of the switch. So we have here VLAN 1 is indicated by a red color. VLAN 1 gets is ports number 1, 2, and 4 are assigned to VLAN 1. Ports number 3, 4, and 6 are assigned to VLAN 2. Now, if you're sending a broadcast packet on the computer into port 1, connected to port 1, these broadcast packets will come out here on ports number 2 and 5, not on 3, 5, and 6. If you're sending an R packet in VLAN 6 onto port 6, that R packet will be transmitted, come out of port number 3 and 4, but none of the red ports. Yes?
Aren't you simply, so before in the first example you had two boxes, right? Two switches that are acting as the subnetwork, and now you're just combining them, right? Where one box basically can send into two subnetworks, and that's basically each VLAN.
Let's see. I want to be the boxes. So here, what is?
Yeah. So each switch is essentially handling all three networks, all three subnets. Where
they don't know what other subnets. They don't know what a subnet is because these are Ethernet switches. They don't even look at IP. They don't get to the IP header. They don't know what. They don't need to know what a subnet is.
So how they grab the packets and say this belongs to port 1 and 2 and this is 3 and 4. I know, but VLAN.
Well, I mean, you're asking the right question. Yeah. So what you're doing is this port is configured for VLAN 1. You're going there, logging in. Instead of you're going into a router, you go into the switch thing interface. Also, if you're having a Cisco switch, it also runs iOS. It just doesn't have routing protocol. You can then go in and configure. You say VLAN 1 assigned to port number 1, VLAN 2 to port number 2, VLAN 3 to port number 3.
Okay, sure.
That's how you, but you will still raise a question if your question is not answered. I get you.
Okay.
There's more to it, but that's essentially what goes on. This is kind of you just configure each switch. This switch is not aware of the existing of other switches. So that's clear. That's simple enough. All right, so here it comes. I think this is what you're sensing is the issue here. So if you now have a VLAN that goes over multiple switches, and that's the example that we saw here. Yeah, we have VLAN 1 is distributed over these 3 switches. If we have that situation, then you're sending now. So if you're having VLAN traffic, VLAN 3 going over here, then you're sending a packet from VLAN 3 onto the switch, and then the switch has to then the VLAN switch then has to know whether this packet has to be sent on port number 123. It's coming from VLAN 3, it has to send it out to VLAN 3. How does this switch know this? Well, that information has to be added. So this is the problem here. This is a similar scenario with two VLAN switches. The colors are, there's the green VLAN and the red VLAN, and this is the assignment of hosts to these VLANs. So the traffic between the switches belongs to different VLANs. The switches need to be able to demultiplex traffic from different VLANs. So if you're sending here a packet from a red or blue over here, then this switch has to act differently. It deals with a red packet or blue packet, red packet or a green packet. So the switch has to know. And that is something that takes place. It's called the Ethernet frames that are sent between the VLAN switches. They have added tags. That's called VLAN tagging. VLAN tagging. These are little pieces, kind of little header information that is inserted to the Ethernet packet, which has essentially the information on the VLAN. So the color red or green is then carried in this packet that is being sent over here. Here, this packet is unwrapped, and you're sending it off on the real port. Yeah, so the packet that arrives at the host, they don't see the tags. The switch is adding that and removing it. Yes?
But these Ethernet frames in that case can only work in the LAN network. You cannot go outside the internet.
They don't go out. This is completely switched. Yes.
Okay.
Yeah, so all of this terminates at the.
So if it needs to go outside the internet, it will go to the router. The Ethernet layer is going to get stripped. It's going to go to the IP layer. Come back.
Goes to the router. So in this case here, this is also a port. This port here will be. This port here will be assigned to any of the to all three VLANs because it belongs to all three VLANs. Now, if so, this switch here, when it sends the packet to the router, will take the VLAN the tag off. It will not send the tag off here. Often, what you have is that you have devices that can perform both routing and switching. Then you can combine them. Yeah. So this router here behaves as if you have a single Ethernet segment where you have multiple, a single Ethernet network where you have multiple IP networks configured. Nobody gets confused. The router doesn't get confused by it. Okay. So the VLAN tag. So the VLAN tag is a packet that is inserted into the full byte of packet that is inserted after the source address. Simple enough. Yeah, and as usual, so the main piece of information is the VLAN ID, 12 bits. Yeah, so you can have sufficient number of VLANs, roughly 4,000 VLANs. And yeah, so that's it. And there's some additional, as always, there's priority information. Things that can be added. Yeah, and so here it is. Let's see. The VLAN tagging, kind of this protocol for adding this, is an addition to the IEEE 802 standard. That's called 802.1q. Remember, 1V was the spanning tree, 1Q is VLAN. Yeah, so if you're looking at an Ethernet switch, it will then say it implements 802.1q. That is VLAN tagging. That's a simple. All right. So there are fields for priorities, and what one can do is one can prioritize different types of data. That is used if you're sending both voice and data. You're assigning a different. This is if you're using VLANs to carry voice and data traffic. And if you're having voice over IP, that means your voice is going over your voice traffic is going over an Ethernet network, then eventually to a router that is going over the switched Ethernet infrastructure, then you want to have your switches treat the voice packets with higher priority than all other traffic, because voice is very delay sensitive. Now, that something is voice is only be apparent if you look at the IP information. Yeah? So you don't want to do that. So instead of that, what is done is, if you're setting, so all the phones, the Ethernet plugs for the phones, they are attached to a VLAN that is given higher priority. So if you say here VLAN 1, these are all voice over IP phones, essentially packet-based phones, then you would assign these phones, this red VLAN, a higher priority. So if you're having a lot of traffic arriving at the switch, you would treat the voice traffic then with higher priority. That's the main idea. Yeah? Yes.
So, I don't know if you said it, so routers can be configured to respect VLANs?
In principle, the functionality of a router and the switch, these are separate functionalities. But you buy a device, if you buy a device from Cisco, if you buy this, the routers that we have in the basement, they're really loud. They're not good as Ethernet switches because they only have 2 ports, two Ethernet ports. That's not a great switch. However, you can run the spanning tree protocol in there. Likewise, if you are, but you cannot do fancy, may not have, Likewise, if you buy a larger switch from Cisco or any of the vendors, if you're buying a larger Ethernet switch, it will have some routing function. And so the functionality of the device is very often combined layer 2 and layer 3 functionality. But functionally, and then you can leverage on that. It gives you some more, gives you some ability to leverage. Essentially, blending this device and this device, you can now decide whether you route or switch. So you don't need this device. You can essentially, if all of these can route at some level, you could just do it. It would not need this routing device. That's the idea. There's always more to it than this complexity. This is the essence of how it works. All right, so that's the priority field. Then the CFI, I don't even know what it is. It's used for complex code. This is the VLAN identifier. It is possible to indicate that the frame does not belong to any VLAN. Then it's even this number 07. All right, so the idea is the packet is sent. So this packet here is coming from a green device. It's going to one of these computers on the right. The VLAN switch adds the tag, carries the packet to the other destination switch, and then the switch, before sending data to the host, is taking the tag off. The protocol, how you carry multiple switches, what your routing is, that will be determined by, the spanning tree protocol. Now the spanning tree protocol builds up the path between the switches, and then I think one runs a spanning tree protocol separately from each VLAN. Okay. So what we have done is we configure the VLAN based on the port number. But it's also possible to have a VLAN assigned based on deeper information in the packet, based on information that is deeper than what an Ethernet switch should be concerned about. So one of them is you can make VLAN assignment based on MAC addresses. So that is to do, when do you do this? Is, if you have traffic from multiple devices going into the same port in the switch, and you want to give this traffic different based on the source the source MAC address, you want to assign this packet to a different VLAN. When does this happen? It happens, just suppose, so the VLAN switch is in the basement. I have on the 4th floor just a regular hub, a regular Ethernet switch, not VLAN, and it's just connecting like 20, 25 different computers, instructors, students, graduate students. They're assigned different MAC addresses. This traffic is now coming through the hub, concentrating the traffic on the same port in the basement. That basement, then you could then distinguish based on the source address which VLAN you want to assign to the traffic, and you can have a different VLAN for instructors, graduate students, and undergraduate students. Some of that sort. Yeah. So likewise, you can do it based on different IPv4, v6. This is something where you're looking past the Ethernet header. You're really looking at the IP header information here. Even port numbers. Yeah, port numbers. So you could have VLAN, a different VLAN assignment for web traffic. Everything that goes to port number 80 is given a different VLAN. So it provides a lot of flexibility. Yeah, it's also possible that multiple VLANs per switch port actually showcase what this is often done. Yes, normally there's only one span tree for VLAN, but one can have multiple trees. This happens because there's a lot of VLAN switches. So if you have a lot of VLAN switches and not all switches serve all VLANs, then having a separate spanning tree has advantages. All right, that's all I have on VLAN. Other questions? Okay, all the minutes have run over. Unless there are any questions, let's just end it here. And Monday, I'll talk about something. I should start with DNS servers. I don't know. On Tuesday, we'll discuss the quiz. On Wednesday, we have the quiz, and then we're all good. You all know when the final is? 9. It's pretty early. First exam.
Yeah. Maybe reschedule it.
I know. Early Christmas break.
My final exam is on 19th.
The last one is maybe.
Somebody has
The last
to
one
get
is 21st. Oh, yeah, that. My last one is 29 and 21st.
我是请他妈的好了，
你就2个？
我就2个，然后一天跟最后一天。
反正考1遍个人像放假一样。考了 PGP 2 ，BGP 2，还有那个 BGP。
这个我感觉我9号考完了，我都可以出去了。
你要不记得都
记得了啊？你听完了？
是不是要前面那个？哎，那个谁，那顾林呢？